This video is about number formatting. It corresponds to subsection 7.9.1 of the Applied Analog Electronics textbook. Now, you've probably had other classes in which you've been representing numbers in scientific notation. And that's an okay notation, but it's not the one we'll be using in this course. What's the problem with scientific notation? Well, you will be writing numbers like 2.2 times 10 to the minus 11. And then you say, oh, and this is going to be, say, farads. There's problems here with getting the formatting right because you need a space in here in order to avoid getting 2.210 to the minus 11, which is a totally different number. And it's just awkward to have little superscripts, particularly the superscripts can get small and hard to read. And it's hard to say, well, I want to pick up a capacitor that has this value. What capacitor is that? And you have to do translation in your head and think, oh, let's see, that's moving the decimal point around stuff. It can get very confusing, and it's easy to make mistakes when you're doing that sort of translation in your head. So we don't use that. There's two things we do. One is to avoid the superscript problem, we use what's called floating point notation. And this is borrowed from programming languages. We would write that number as 2.2 e minus 11. Capital E here so we don't get it confused with the lowercase e that we use as the base of natural logarithms. And this whole thing, you don't want to do it in math mode, or if you do have to do it in math mode, so you're in math mode, go to text and put the number in ordinary text. And then you can have the rest of your formula. And the reason is we don't want this read as 2.2 times capital E minus the number 11, which is the way LaTeX would format it if you just handed it to it as pure math. If you're just in text, not in math mode, just typing this thing normally will look fine. Okay, so even that's not quite what we do. So the floating point notation gets rid of the superscript problem, but it doesn't solve another problem, and that is figuring out what does this mean. Sorry, we should always have units. What does this mean in terms of how many farads is that? And for that, we're going to use what's called engineering notation, which is a special version of scientific notation in which the exponent is a multiple of 3. So basically we're only using powers of 1,000. And so we would write this one as something like 22 e minus 12. And when we're doing this engineering notation, the exponent being a multiple of 3, we also will have a further constraint, and that is that the number in front is between 1 and 1,000. So that we took this thing to 22 e minus 12 rather than 0.022 e minus 9. When we've done this, it becomes very easy to convert something like this many farads into the notation we'll actually use, which is not engineering notation, but notation with metric prefixes. We would write this thing as 22 picofarads. And now that's very easy to use when we're looking for a component because 22 picofarads is a size that we could look for in a catalog. It's something we could look on the part markings to see, oh, it's got a 22 on it, that's 22 picofarads, we're all set. So that's the notation that I'm going to expect to see for all component values. Anything which has units, I'm going to expect to see it with metric prefixes. And the metric prefixes we use are only the ones that are powers of 1,000. So that's the correct notation here. So that's what we want to see. We do not ever want to see something that's got scientific notation, even worse, scientific notation without proper spacing. Those are just absolutely out of the question. Now, there is a time when we don't get to use metric prefixes, and that's when we're dealing with a unitless number, like the gain of an amplifier. If you have output in volts, input in volts, the gain is volts per volt, which is unitless, and so we can't talk about a gain of kilo something. You could talk about volts per millivolt, but that's a little awkward, and so most often what people do with gain is to just treat it as a unitless number, and then you would use engineering notation. So if you had a gain of 2,200, you would either write it as 2,200 or as 2.2 E3. And either of these are acceptable, and it's largely a matter of taste which one you choose, so I'm not going to be fussy about that. One important consideration here is if you ever decide, hey, I need to have a number that's less than 1, but I don't want to go to the milli prefix or something like that. So if I've got a gain of 0.1, something like that, you must have that leading 0. It is absolutely forbidden to write a number starting with a decimal point. Why? Well, decimal points disappear very easily, particularly if you're writing in pencil or writing on things that you erase. It's very easy for that decimal point to appear, or for you to be writing something and put the 1 there, and there was a little mark on the page that looks like a decimal point. Is that a 0.1 or is it a 1? It's hard to tell. And so we're going to just simply prohibit any of this. You must always have that leading 0 if you've got a number that's between 0 and 1. And one of the nice things about using engineering notation and metric prefixes with this constraint that you're putting that number out there between 1 and 1,000 is that you never have to deal with leading zeros because you don't have any. You've always got, oh, if I want 0.1 volts, I'll write it as 100 millivolts. Occasionally, because you're doing a lot of stuff in volts and you've got one number that's just a little below 1, and you want to say, okay, I'll do this one still in volts, then you'll do 0.1 so as not to have to switch to millivolts for just one out of one number in a table or something like that. But when you can, keep your numbers between 1 and 1,000. One other little thing. If you're grouping numbers, don't use commas to separate thousands. So I don't want to ever see something that's written like 2,200. Why? Well, one problem is that sometimes, particularly in handwriting, commas and periods are hard to tell apart, or in small fonts. And then, is this 2.200 or is it 2,200? I'm not sure. Furthermore, in a number of European writing systems, the comma is used where in America we use the decimal point. And so this would be 2.200 and not 2,200. So I never want to see commas. So don't do that. If you have to do grouping of numbers, use a thin space. Oh, the way you write a thin space in LaTeX is with \comma. So the thin space is useful if you're trying to group something that's got 12 digits in it or something, and you want to group them into groups of 3. Use a thin space between the different groups. And it's also used to separate numbers from units. So when I have 2.2 e minus 12f, the way I would write that in LaTeX is with a \comma here, and 22 picofarads would have a \comma here, so that those have a thin space rather than a fat space between the number and the units. That also has the advantage, if you use a thin space there, that the thin space is not breakable, so you won't get a break at the end of a line, so you have 22 at the end of a line and picofarads appearing on the next page. I have seen students do that. It's really, really hard to read things where the units are on a different page from the number. So using the thin space to separate the number from the units has the advantage of getting rid of the breakability of the space and keeping the numbers and the units together. Okay, that's probably all you really need to know about number formatting for now. I'll be watching for it in your homework and in your design reports. If your calculator has the ability to set engineering notation rather than scientific notation, I recommend you do that.